Hello, everybody. Welcome to my talk. My name is Andrei Kostin, and I'll be presenting Dangerous Pyrotechnic Compositions, a very long title. So, as you can see, it's the holiday seasons. I specifically choose every city I go fireworks image for the city I go to. And it's interesting because in 2 days will be a big fireworks and celebration in exactly this place. So a little bit about who am I. I started with RFID security, and by the way, can you raise your hand if you've been visiting my last year talk where we were unofficial free ride for Bucharest presenters? Okay, good to see you. Thanks for coming back. I used to do some printer embedded research, CCTV embedded research, airplane embedded research. So basically, I'm mostly embedded security from the software side guy. I'm doing my PhD in the topic of embedded security. And lately, I've been looking for the firmwares and fireworks, and basically, if you look for fireworks on Google Images, it brings these pictures up, and it's nice because FW also means firmware in many abbreviation or documentation. So firmware and fireworks kind of hit on the same topic. I find this interesting. Just before we start, a small disclaimer is this is purely educational and research purpose, only presentation and demo, and we, myself, and our university have no liability whatsoever on the speaker or affiliates. And because it's a real cyber-physical system, it brings high accident risk and life hazards. And we advise you to play, but do not replicate unless qualified or equipped and so on. So it's the basic disclaimer. So how this research started, I'll do a little bit of introduction. So we started with a large-scale analysis of embedded firmwares. So in a nutshell, what we did is that we built up a system, which you see in the diagram. It just goes on the internet. We have simple crawlers, crawl a big bunch of firmwares. We crawled around 4 terabytes of data. Some of them were not firmwares, but we had like 800,000 files we used for our academic publications. We analyzed like 32,000 of them. And just by doing simple analysis, we found 38 vulnerabilities in more than 600 firmwares. And just a simple check showed up that at least 100, 200K online devices were affected. So it basically was a first large-scale comprehensive study on the firmwares. And why it was interesting? Because the firmwares are basically the lifeblood of any embedded device. If you have any desktop or server systems, you most likely have a Linux distribution or Windows where you have a streamline update, where for embedded devices, those devices say if unsecured or unpatched, and the software and basically the firmware for them are not your usual suspects, right? It's not exactly as in the desktop world. This is a spin-off of our academic research where we put up a website, basically a web service for researchers or pen testers or whoever is interested in doing embedded research, where they can upload a firmware file and our system will run the scans on them. It's called firmware.re. And the good thing is that we are building up some features into it, and you can see that basically without having any knowledge, you just have the firmware of your interesting device. Let's say it's a photo camera, it's a home router, it's a printer. You come, drag and drop. Most probably we'll be able to unpack, give you the unpacking tree, and then do some analysis like whether it's encrypted, do some entropy analysis, and we have a bunch of our features which we are working to as a research, but are not yet deployed. So the idea is that you don't need to install all those many tools like many of you heard about Beanwalk or many others. Sometimes they are cumbersome to install or use. We just provide an easy, clean interface. And it's a win for everybody. We win that we can help you, and you win because you don't have to lose time. So some of the example of firmwares you can find on, or CVEs you can find on our site. You're welcome to check it out. So this was a small introduction on how we did, what we did, and what we are doing, to give you a sense that basically we swept the internet, we got a lot of firmwares, and the interesting thing is that in one of those firmwares, so basically we build up some static analysis, mainly static analysis tools and scripts, and we found that in our database we have some .ihex format, and if you know ihex or srec, Motorola srecords, is basically some text-based format for embedded devices, used to be uploaded to microcontrollers, and basically is the software binary of the firmware encoded as text. And after some automated analysis, we found some unencrypted firmware inside this ihex, as most of them are. And the funny thing, okay, we did some more analysis. We found that it's a Motorola 68K based code. So basically it's a free-scale derivative of it. And oh, it has debugging features. It has different debug and console ports, and basically, okay, but we don't know what it is because we have so many firmwares, a lot of things pop up and you have false positive or just things which are not interesting. We also found wireless protocol. So it's like, you know, some average device could be. However, when we did more analysis, we actually found out that it's a firmware for a Pyrotechnic systems, or what is called a wireless firing system. What does it mean is that whatever you see as a pyrotechnic show, okay, whatever explodes in the sky, is only the top part you see of the whole process. The whole process of a pyrotechnic show or a wireless firing system, and why it's called a wireless firing system, because it's not only pyrotechnic shows to make you fireworks, it's used for military simulations or just triggering some explosives at building demolition. When you have a building demolition, you have area being cleaned off of people, of objects. You have the explosive installed in the building demolition, and then it's remotely being triggered. So that's why it's called wireless firing system. It brings fire remotely, right? So what you see usually is only the top side, but then the whole process is like that. The top side is being thrown into the air by the tubes, and these tubes are called mortars. And inside the mortars, you have the display shells, basically some spheres, which are called the pyrotechnic composition. It's actually the mix of pyrotechnic material, which when ignited or detonated, produce the visual or sound or visual plus sound effect, which you see during a pyrotechnic show, for example, for New Year. And in order to fire these things up from the mortars, right, you need some kind of signal to start the fire, and this signal travels through the igniter or fuse clips. It's basically some special wires. Okay, it's not very special, it's just copper wires. However, at the end of these copper wires, in the middle you see some finger. It's a clip, and the clip has a fuse which basically receives a high amperage current, and it makes like some sparks, and these sparks basically start the fuse and the detonation process. Okay, but how does this current is being pumped into? Okay, it's being pumped by electronics, right? I mean, it's current and it's some circuitry. Before it used to be like that. They had to pull for all the pyrotechnic shows, and it's still used the whole technique where they have to put like hundreds of different pair of cables for each of these tubes. And basically because you need to switch every tube on once, right? Because it has only one explosive inside. And if you have a huge fireworks show, imagine Dubai or any other Asian country with a big budget, you'd have basically an array of hundreds of these tubes. And putting wires and checking continuity on all of them is error prone, is cumbersome. It can lead to some circuit loss. And then if your circuit is lost, then the fireworks is not performing as expected. If you expect it to have a heart in the sky and some wires are broken, when you don't have a heart, you have something else. So one of the reasons to overcome this wiring mess is like exactly in the networking. You had this Ethernet mess, and people started to move to wireless. It's the same here. A lot of wires, big problems, hard to maintain, a lot of problems. So they started to do the wireless firing systems. So what's the idea is that basically you remove all the wires, you have some boxes which are called firing modules, and these firing modules, which you see, they have basically an array of 60 or 32 or 48, depending on the performance you need, of wires. And basically it can receive 48 different channels, so it can fire 48 different. And by putting 10 of these on the fields, you can build up an array of wireless tubes, so to speak, like virtual wireless tubes. And how are these tubes being controlled? They're controlled through the remote control module, basically what you see down. And this is the main thing which is a pyrotechnic engineer is carrying in his pocket, let's say. And once everything is set up and is checked, he takes this remote control, he goes to the safe distance, like 1 or 2 kilometers, depends on the geographical and country legislation, because different country has different safety limits. So he goes away and then starts pushing the buttons. You can see the below has some buttons, and the signals will go on. Of course, this can be done manually, and this can also be done automatically, where there are some scripts, and you can script the show so the tubes fire in the right timing, so you get a nice show, green, red, whatever you want. So in general, the normal or safe mode of operation of such systems is as follows. The pyrotechnic operator connects the firing module to the pyrotechnics and wiring. As you can see, it has a lock on the top, in the middle. Can you see it, everybody? Is kind of a lock, because these firing systems, or everything related to fire, has to be double secured. Basically, you have a physical control and a digital control, because it's the regulation, it's the global regulation in this kind of systems. You need a physical check and the digital check. So they have this key. You see, it's off, it's test, and it's arm. So on testing is just to check if the system is running okay. On arm, it means that it's ready to fire. Basically, it will pump the current. So the operator will turn the physical key to test, will do the continuity test that all the wires are fine, all the LEDs are blinking, all the frequencies are okay. Then, once it's ready, it will turn to arm, and firing module is now physically armed, and it's waiting just for a digital arm. It means like a digital signal. It just needs a specific packet, okay? It's simple as that. And the operator departs to safety distance. Once it's on the safety distance, the operator takes the remote control module down. It has also a key in the middle left, and turns it to arm and press the fire keys, and it will send the expected digital fire command, which will fire the things. So you can see this is kind of just a screenshot. I'll have also a video demo where you can see that both are in arm position. They're on the same channel, because there are some different channels. It depends on the vendor, like frequency channels. And you see that on the remote control, I'm pressing the second tube. And on the firing module, you see the LED of the second, you see the LED? So once you press the second tube, it will fire whatever is in the second tube. So in this way, it just was a very short tour of how these wireless systems work, how they work, and why it's like that. And interestingly enough, wireless firing systems are a good example of two types of devices. First, it's a wireless sensor actuator networks, because it's basically a widespread peer-to-peer wireless sensor networks, and it's actuator because it makes some actions on the Pyrotechnics, and it's also a cyber-physical systems where any action in the cyber domain, in the cyber world, digital world, will have a direct effect in the physical world, where you can create a fire, you can create a damage. So it's not just I can infect your PC and that's it, you just reinstall your PC. It's basically a real one-to-one translation to the physical world, and it's damaging. So again, it's used for different kind of scenarios. So what we did, once we found the firmware, we checked the string, we run our scripts, our tools, and we figure out that the system might be vulnerable. False positives are bad because it takes a lot of time to check something, and it also, false positives are bad, especially in the embedded world, because if you think a false positive is a vulnerability and you buy a device and it's not vulnerable, then you spend your money and time for nothing. In this case, we were pretty sure it's vulnerable, so we bought the device. You can buy these devices online. There is no particular restriction because these devices are not explosive. It's just the device to action the explosives. The explosive, you have to have a license, maybe. So we bought the device, we disassembled as well to confirm our findings. In the device, we saw the Zigbee antenna, if you know the Zigbees, or A02.15. Okay, or they have a JTAG just to debug the things. You see the main MCU, this is the Freescale Motorola chip. And you have some USB, some UART ports. So basically you can do a lot of debugging. And these things are there on the board just in case something goes wrong on the field and they need to fix it. The same on the remote control. There's an antenna, a power connector, there's the Zigbee module, and the UART where you can connect to the serial and have a console on the firing module. So it's kind of being root console on the firing module. I think it's funny. So doing more analysis, again, we found the specific type of processor is not interesting right now. Then we found that this particular of Zigbee chipset are using the 8 mega 128 RFA1 chipset. It's very commonly used in open source projects, if you're familiar with pen testing the Zigbee or 802.15.4. And basically these particular devices were built on a development kit which comes from Synapse, and it's a big vendor of wireless Zigbee solutions. It also has a Snap network operating systems where you have Python bindings and remote procedure calls over Zigbee network. So it's kind of whole new world. It's a lot of interesting stuff. And this particular chipset, by the standard, by the 802.15.4, they support the AES, basically the encryption, or you can use also as a signature of packets and so on and so on. It's supported, but for some reason, I can explain why, these kind of systems or this particular system vendor didn't use the AES encryption or signing. Why they don't use is twofold. Is that for them, the importance, encryption brings additional computational overhead, and sometimes the encryption can lead to corrupted packages, and those packages will be dropped. So it means that if you need a very precise timing and sequence of the events or explosions, for example, imagine a building demolition, where you need specific thing to explode at a specific moment and the right order. And if you skip one or two of these events, it's worse than having something in the clear text. So this is one of the reasons why these kind of critical systems, they don't use encryption, even though the chipset has it, right? It's a trade-off. It's a trade-off of, the other problem is that they could use the signature, but okay, it's another problem. So one of the attacks, very simple, is like that. How it works is that the attacker has this kind of a device, which I'll present quickly down. It used to sniff, replay, and inject in a loop. So basically, it sits nearby the fireworks venue or explosion venue, and it waits for the systems to be set up, and it just listens and sniffs and capture the packets, replay, and inject. the system or the victim, basically the pyrotechnic operator, he doesn't know there's a rogue device. He connects the firing module, again, does the test, then put it to arm position, and the arm position is on. So the only thing the firing module awaits is the digital fire module command. And because we have this thing down which sniffs and replay in a loop, as soon as it saw the presence of the devices, it will immediately send the digital fire, and the guy who just turned the switch to arm will not have time to leave the premise of the explosives, right? Because he's near the explosives, he turned the key to arm, but the device, the attacker device, is in a loop somewhere nearby, and it just sends the digital fire. So it basically, this kind of attack and this flaw kills the entire principle of segregation of physical and digital, because the guy doesn't have the time to leave the safety distance. So for our attack, we used Telos B. It can be used with good fat or killer B firmwares. If you don't know or know just a little bit, I invite you to check these two projects. Good fat should be a really good start. There's also some from Synapse, their own kind of a device for reprogramming or sniffing. For injecting or replaying, we used the Econotag. It's the same chipset as used in the firing systems. And yeah, it's, I'll show you how it looks. So this is a screenshot. I'll try to show you the demo. It's a screenshot of the sniffing, and this is a screenshot of sniffing with vendor-specific software and stick. So this white screenshot is from the software of this Snap device, and the black screenshot is from the Telos B. Okay, so, and the theory, the ultimate attack for this kind of devices, and if your company has enough money and wants to implement this in practice, please approach us. The idea is like that. Usually these systems are kind of air-gapped. They are not supposed to be networking anything. And these devices have also some USB connection, because sometimes they need firmware upgrade or to put a script to execute the show. And basically, with these rogue devices, we can send different packets to both firing and remote control modules. So there are two, the remote controls and firing. We can send the packets, and these packets reach the ZigBee interface, and this ZigBee interface has GPIO, general purpose input-output, to the main processor, which means that you can basically reach the main processor and reprogram it wirelessly, right? Or inject firmware or rogue code wirelessly. So you infect the ZigBee of the firing and remote control modules. It reaches the main MCU. And once the operator, who never connected these devices to any network, just puts the USB, you infect the USB, and then you can travel to other devices of the same family via the wireless mesh network, or you can even reach the corporate intranet or whatever. So at the end, with the disclosure, we took it responsibly. We contacted the vendor. It was a little bit hard because the impact can be huge. We published a white paper, but we didn't disclose too many technical details, not to make it like a script kiddie. But the vendor confirmed the issue and had security improvements being deployed. And basically, we received an email that, because we're a customer of the vendor, we also received an official email that there is a patch and you should upgrade and so on. So we're kind of happy that we pushed to the right directions. Okay, so there's a lot of future work. You can check into the slides. I just want to show you the demo, because I guess we are short in time. And if we have time, I'll get back to this. Okay, so what you see here is okay, we'll just start the sniffing with the Telos B. You see it's a few lines of scripting, and I'm using the good fat. Everybody can see in the back, is okay? Or is not very... captura e la... Nu, e captura făcută la... Ok, just one second. It's worse, huh? It's worse, right? Just one second. I'm sorry, the capture was in too high resolution, so... Okay, sorry about that. So you can see the Telos B. This is the Telos B, which I'll be plugging into the USB hub. You can see the devices down. Okay, the firing module. So here's the remote control and the firing module on the server side. And they are both off now. And I plugged just my Telos B, which is, I explained I use as a sniffer. I just run, as you can see, here's a small command which says good fat cc spi sniff on channel 15, and basically also dump everything into a temporary file, which why I dump into a temporary file you'll see. And in the other console I also do like, because these packets are hex, ASCII hex encoded, and we want to make them more text readable or human readable. So you see that I turned on the device, the remote control, and the sniffer down, it started receiving some packets, and up is a textified of these packets, and you can see, I hope you can see, the remote ping, kind of. It starts pinging to see if there's any firing module present. So you see it starts to blink all the LEDs, basically doing a built-in test. Now I also started the firing module, farther left, and you can see there's some other packets, and it also sends a remote ping. And basically this kind of two devices is because it's a mesh network, they start to ping for each other and try to find each other, and you can see now there is a ping reply. So after they both are on and finish the built-in self-test, they say, okay, I'm ping reply, and here we go. So this is basically the sniffing. You have to synchronize the channels. I synchronize them on channel 3, and my fingers are showing now there's the arm LED. Basically what it means, it shows that when you arm a device, like they show, yes, we are armed, we are ready to fire. And just one second, we'll see that you saw there was come on. Just one second. And you see basically in the middle of that screen is acknowledge armed. It basically, the firing module, it acknowledges that it's armed now to the remote control. It says, yes, I'm armed, I'm ready to fire, okay? So you can sniff all these kind of messages, analyze them, start to replay, inject. So you can see that you can say, yeah, I'm this kind of a device, please reply to me. Can you arm yourself? Yes, okay, you're armed, fine. So this is two legitimate devices. And basically, you see that I'm pressing some buttons. If you look closely, I'm pressing some buttons, and basically it fires up the LED. Can you see it? It fires up the LED. So what it means is basically if there was an explosive connected on that wire, it would fire up now. What I'm doing now is I'm connecting the Econo tag, which is basically the injector or the replayer. And you can start seeing that I'm not pressing any buttons on the remote control, but the LEDs are bombing everything now, right? As soon as I started the Econo tag, the firing module is receiving bomb everything, like fire all the wires, right? So I show that it's as easy as just changing few lines of code. If you want a different bombing patterns, I replace the bomb ball with 31337. The friends know why. And okay, there's a compilation error. It's not 7, it's 7. Okay, we make it 31337. We compile the source code, it compiles. You see, it's not big deal to compile a firmware for an injector. It's just having a default thing. Make file, you compile. It will take some time because when they are two connected through the USB, they collide on dev TTY as so basically what I'll do, what I did is I disconnect the sniffer so it doesn't collide for the USB port. I just replug the Econo tag and I try to refresh it again. Now it's being detected. And you see some dots, it's waiting for the firmware upgrade to go through the serial. Okay, it's sending now the firmware. And you'll see now that, okay, the last reboot after and it starts sending the things. So you can see now is 1337, 31337. Basically, I can do whatever pattern I want, or I can bomb everything and so on, right? So you can see how easy it is just to compile this kind of a firmware. So I just wanted to show both how easy it is to compile and things, and the last one, which is, well, more interesting because you can see the actual thing. So I take the previous example with 31337, and I replace it again with bomb all. It means that we'll send the fire signal to everything. Okay, you can see that I'm showing I have a wire connected to position number 1. And the wire is a special wire with igniter clip. And at the end of the igniter clip, I put a match and I insert it in a bottle just to make sure there's no fire and stuff. And you see that I'm starting up the modules, they synchronized, and I just plug in the Econo tag, basically the injector, which will send bomb ball, which will send fire me anything. And keep attention on the bottle. You see the bottle, the part of the bottle? So you'll see that the bottle and the array of LEDs, right? Because all the LEDs will turn red. And the bottle, if you, okay. You saw that there was a fire, okay? So basically, when I take off and you see that bomb ball is going every second. I can make it go continuously or randomly or so on. And when I take off the match from the bottle, it is burned, is black. So it's for real. I just don't want to put real explosives because when we don't have a university. So, I mean, I hope to make a better capture, but you see it's like a burn, it's a black one. You can trust me. Well, so that was the demo. Unfortunately, I cannot bring this kind of devices easily through the airport security because I get asked different questions, which I really don't like answering, or at least not get those kind of encounters. But yeah, I'll have a better demo with more 4K HD resolution, whatever. Um, okay, so to resume, is conclusions is that firmware analysis gets better and faster, and basically this firmware.re project, which we are running, proved us that we can just take any random firmware and we can run simple analyses or techniques and get us really precise clues where to look in order to find some vulnerabilities. Check it out, drop me an email, I try to help. It's still a building up project, but we try to do our best to give as much as possible. Another thing is that wireless security is an issue in many products, and it's even a problem for life critical systems. And you can see that it's still vulnerable to basic attacks like injection or replay, which shouldn't happen. But because it's hard, yeah. And well, firing system security must be taken seriously because it's like you can have a direct impact. It's probably involves certification regulation, but again, I guess is not up to the technical people, is more to the legislator and regulators and so on. And I really like this one because with all these weaponized exploits naming, I really think that fireworks and cyber physical systems hacking is actually putting the real meaning of weapon into the weaponized exploit concept, where you can have real weapons based on weaponized exploits. You can see the white paper on the wireless systems with all the details, all the pictures, all the schematics and so on, and our firmware analysis paper. And yeah, I hope you avoid situations like this where people just get bombed by fireworks at random places. Yeah, thank you. Feel free to contact me.
We have time for 2 questions. But first, I will switch 1 second into Romania. Cineva cu o mașină B900 CHI, un Range Rover, a parcat greșit, a blocat pe cineva, așa că vă rog. Cineva? Înseamnă că nu aici. Okay, sorry about that. Questions?
Hi. It was a really great presentation. Hopefully we won't be near fireworks today.
Thank you.
Yeah. My question is about the range. You said that the safety distance is usually 2 kilometers. And what kind of Wi-Fi signal they send? Obviously, your echo thing won't work unless it's very high power. Is that correct?
It's a very valid question. First, the 2 kilometer example was just an example. If you have to go to the regulation of each state or each country to know exactly what, because there are class A explosives or fireworks, class B, it depends on the power and blah, 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 and many other things. So it's like a table with different safety distances. So I don't know those distances by heart because I'm not a regulator, I'm not interested, but for different systems, you have different kind of devices which will achieve this range. This kind of a device is class C, and I guess it works up to 300 meters, as far as I remember. It was like 1,000 feet. It still works, so, well, I don't know how they particularly achieve the synchronization with the power, the distance, and the regulator distance, but I think they work something out. Anyway, you can severely damage the crew if you really want, but yeah, another thing is that even if the crew is departed, and you bomb all the explosive in one go, because the good thing about fireworks is just go one and one and one. But if you accumulate all the detonation power of everything in one go, the impact is huge, right? I mean, it's not exactly as detonating one by one. So I guess this one is for 300 meters, like 1,000 feet from their specification. Yeah.
Right. I know you didn't work on this side, but as a guess, how likely do you think that the same kind of issues could or be realistically exist in smart munitions, as in missiles and smart bombs and stuff like that.
Yeah, we didn't look at these smart munitions, but from what we see is the things are going into that direction. We have some samples, but they are encrypted. We are working on it, and most probably we'll
So
find
at
a
least-
way.
So at least they're encrypted.
Yeah, at least they are encrypted.
Okay,
That's
okay.
true. But yeah, the thing is that it's going into that direction of yeah, of smart guns. Let's say it's a very broad topic and a hot topic. But we cannot say whether the issues exist, but more probably they will exist, or they exist maybe in a different scenario or setup, maybe a little bit more protected. It was like an easy target because we did it almost automatically. Maybe it would require more manual analysis, but definitely I suspect they exist. That's why we were looking at these cyber physical systems, and yeah. Thank you again.
Thank you so much.